Saxon Advanced Algebra, Lesson 40. This is a two-parter. Yeah, I'm going to call it a two-parter. The ideas kind of blend together. But the first thing we wanted to talk about is something called the argument of a function. Argument is one of those weird words in math that we all know what an argument is in real life, right? It's when two people are shouting back and forth at each other and usually have extremely different matters of opinion, and they're not happy with each other, right? In mathematics, when we talk about the argument of a function, it means something completely different. There's no anger, there's no back and forth. An argument is simply the values put into a function. Oh, we have lots of different words for this. Sometimes we call it the domain. Sometimes we call it the inputs. Sometimes we call it the independent variable. Oops. Right? We've used a lot of different words that mean, they don't all mean exactly the same thing, but I don't want to split hairs over this. They mean more or less the same thing. How do we see the argument of a function? All right, well, what if we say y equals the sine of x? There's the argument. That's the argument of the function. What if we say that the f of x, okay, this time we're going to use more function notation than we did the first time. The f of x equals the cosine of 2x minus pi. Well, that's kind of a mouthful. But again, this is the argument right here. We can find it easily in problems just by looking at where would you, it's kind of like where's the x, right? Or similar variable, where would you plug in a value? Here's another one. The g of theta equals the tangent of theta over 4 minus 30 degrees. These are just random choices. But again, this here is the argument. It's not just the letter itself, although we can see there's where the real input happens, right? But we have to do a little bit of work on that, right? It's not just x, it's 2x minus pi. This whole thing is considered the argument, and this whole thing is considered the argument. We're not going to work a ton, we're not going to fine point this a whole bunch, but this is going to come up in our conversation around logarithms, which is what we're going to turn to next. So put this in the side of your brain, not the front, but not the back either, and we're going to come back to it in just a couple minutes. Okay, now let's talk about the laws of logarithms. We talked about these last year, right at the end of the year, and you probably don't remember a ton. We say that logarithms and exponents are two sides of the same coin, right? So let me prove that to you. The way I'm going to do that is by drawing a nice big chart. Draw it with me. I'm using about half the page, so I invite you to do the same. And you're going to want to put this in your notes today, but you're also going to want to pause me and write it wherever you write your formulas. The first column should be the smallest, then this one sort of medium, make this one the biggest. And then here, we're going to make 3. There's 4 in all. Make 1, 2, and 4 about the same size, and make the third one a little bigger. I'll give you a second to catch up. All right. When I do the first part of this chart, you're going to roll your eyes, and you're going to sigh, and you're going to be like, oh my gosh, she's talking about this again. I am so sick of this. I know you're going to think that, so it's fine. Go ahead, think it. But then I'm going to take it another step. We have something that we call the product. Whoops. Rule for exponents, and that's what this first column is our rule for exponents. And you know, or at least I pray that you know, this rule, which is if you're multiplying a base with an exponent times the same base with an exponent, you can combine them by adding the exponents. Okay? When you multiply the bases, you add the exponents. Now, let's see how that plays out in our laws for logarithms. They look a little bit different, but I'll help you find the important parts that match. If we have a log where we are multiplying in the argument, whoa, there's that word, we can take those two logs and put them into separate arguments and add them. So when we're multiplying in our argument, we can break it apart and add them as separate logs. Just like with this, we can move in either direction. If we've got this and we'd rather have it written together, we can do that. If we've got it together and we'd rather take it apart, either way works just fine. So this is the product law for logarithms. And the next one is called the quotient. Here, we're dividing, right? We're dividing matching bases with different exponents, and here we subtract. Top minus bottom. That's our rule for exponents. This is the part that makes you sigh and go, oh my God, whatever. I've seen it 100 times. Now here comes the logarithm bit. Log b, and here we're dividing in our argument, and we say that's the same as if we subtract separate functions, right? So it's the same idea. Division can change into subtraction, right? Division and subtraction are linked. Multiplication and addition are linked, all right? Okay, so far so good, right? You see the parallels? Now comes the power rule. This one is the one that where it's hardest to see the pattern, but it's the most fun to use. In this one, we say if you've got a base with an exponent and you're raising it to a higher exponent, we multiply the exponents. Now, here's the logarithm version of that. If you've got an exponent on your argument, you can take that exponent and jump it in front of the entire function. Look at that. We took that n from being an exponent and plopped it out at the very front of the logarithm. Huh, that's weird. It's the hardest one to see the pattern that matches here. But this one is really fun to use in the problems that we're going to do. Okay, so we talked a little bit about the word argument in that what we're doing here is we're changing the arguments, right? That's part of the way that we change these. Here we've got multiplication in our argument. We can add them as separate logs. Here we've got division in our argument. We can change them into subtraction. Here we're raising it to a power. We can take the exponent out of the argument and put it at the front as a coefficient. Crazy. They parallel these rules for exponents, and just like I've said that exponents and logarithms are two ways of saying the same thing, that's why these laws look so much alike, and that will help us remember them. One more thing I want to say about arguments in logs. Arguments in logs must be positive, whether they're individual, no, these are the individual, or combined. This has to be a positive number. John is not really going to torture us with any situations where they aren't positive. That's not going to be a trick that he plays on us, but it's an idea I want to plant in your head so that later in a different class, when you may have that problem, you will be ready to handle it. Okay, let's do our first problem in this little space here. It's example 40, sorry, 40.1, and it looks like this. I'm running out of room, so I'm squishing. The log b of 4 plus the log b of 6 equals the log b of quantity x plus 4. Okay, so how do we do something like this? What we try to do is, step 1, we want to simplify each side to a single function. That means where we have this plus and we have two functions, we don't want that. We want to try and smush them together and have one log on the left, one log on the right. Now, how can we take this and smush that into a single log? Aha, this, we have the tools. We're adding, so we can rewrite that as log b 24, 6 times 4, equals log b x plus 4. Now, let me just point something out. Log b, what does that even mean? How can we have a base that's not even a number, it's a letter? Guess what? It's fine. It doesn't matter. When we have really random bases like that, your takeaway is, I'm not actually going to calculate the logarithm. I'm going to do algebra on the functions until I solve for x. But I'm not going to need to, start clicking numbers in my calculator because we don't have a log b, right? So if you see a problem with a base other than 10, which is sometimes written as nothing, or the natural log of e, then that tells you, oh, I'm not calculating a value of the log per se, I'm calculating the value of some variable that's been tossed into it, all right? So that's our hint that, oh, we're just doing algebra on this. All right, so we used our product rule, our product law. Logarithms get to have laws. Exponents only get rules, right? So, logs are special cool like that. Now, here's the next step. And I like to explain this without using a bunch of mathematical terms so that you can see it really just crisp and simple. We've got one log on this side and one log on that side. Once we've achieved that step, then we can take the two arguments and set them equal to each other. Because if the logs of these two values are the same, then the values themselves have to be the same. That's a hard idea to wrap your head around. I'll keep saying it as we go on. But once you get each side of the equation to a log with a matching base, and it's just a single argument, then you can pull it off. That's what I said here. Pull the arguments off, and we will simply have 24 equals x plus 4. So easy, right? And we subtract 4 from both sides, and we get x equals 20, and that is the correct answer. All right? So most students, even if they find logarithms kind of annoying and overwhelming and using the buttons on the calculator, these problems where we're using algebra in the arguments to simplify and solve for a variable, right? We're not finding the log of 20. We're just saying 20 is the variable in this number, and we're using these rules to manipulate the logarithms algebraically, but we're not using buttons on a calculator. Okay, let's do another one like this and see if it makes sense to you. 40.2. We have 4 of these problems now. Here comes the next one. okay? Again, as I'm writing this down, I'm noticing that the base is 4. I don't have any base log 4 buttons on my calculator. Obviously, I'm not going to need them. So what we're doing is not actually calculating the logs. We're using the laws of logarithms to solve for these variables, these x's floating around here. Now, what can we do with this one? Again, our goal is to turn each side of the equation into one function, just a single argument. Here's our problem. We have 2 over here, and we're subtracting them. This side looks fine, right? This is just 1. But we've got to do something to combine those to make just a single function with one argument. Then we can take the arguments off and solve. So here's another copy of my rules that I have. And we see this time we're subtracting, so we go, oh, it's the quotient law. We want to use this one. So what that tells us, if we're subtracting, then we can take the arguments and divide them and write it as a single log. So it will be log of 4, the base stays the same, but it'll be x plus 6 divided by x minus 1. And if our arguments get complicated, we put parentheses around them, equals log 4 of 5. That is unchanged. That one was cute and perfect, right? All right, now we've got each side. If you wanted to make these parentheses individual ones, that's fine too. This sometimes looks weird to people. Now we have a log over here, a log over here. Now we can pull the arguments and write x plus 6 divided by x minus 1 equals 5. We'll cross multiply, and we will get x plus 6 equals, and I'm going to distribute that 5 across as I multiply, 5x minus 5. And then let's see, let's add 5 to both sides, and let's subtract x from both sides. That cancels, 11 equals 4x, and then we'll divide by 4. X equals 11 over 4. Again, that's an algebraic answer. We use the rules of logarithms to solve it, laws of logarithms, sorry. But we did not have to actually calculate the logs of anything. We were simply solving the variables in the arguments, all right? So this is a different kind of log problem than the kind where we actually solve. Okay, 2 more. So first we used, let me show you. First, we used the product rule, and we had 2 logs that were being added, so we combined them by multiplying. Then we had 2 that were being subtracted, so we combined them by dividing. Golly gosh, I wonder what might happen next. Let's look and see. 40.3. It says, again, I noticed that my base of my exponents is a b. At first, that makes me feel really weird, and then I realize, oh yeah, it doesn't matter. I'm not calculating a log. I'm solving for variables in the arguments. And I am going to need to use that power law, aren't I? Right? Because let's see. We can see here we've got a coefficient, and we're going to want to get rid of that coefficient because we have to turn both of these into a simple log expression. So here's what we've got, right? We've got a 3 out in front, so we're going to jump it up and put it as an exponent on our argument. Oh, that's so weird, isn't it? So it becomes log b x cubed equals log b 8. And now that both sides are equal to logs, in this case, this was a single log function, but it had a coefficient. And that's what we have to clean this up before we can have them like this. Now we can pull off the arguments. X to the 3rd equals 8. And we take the cube root of both of those, and we get x equals 2. Yay! Correct answer. All right. And then we have one more problem before we switch topics. And this one is we see it's log 12, base 12. Well, that's disturbing, but again, we put our weirded out intuitions aside and say, no, it's fine. We need both of these sides to be nice, clean log functions so that we can set the arguments equal to each other. This one's beautiful and perfect. This is a problem. We're going to use the power law again to pop it up as an exponent on this argument. So it will become log 12x equals log 1264 to the 2/3. Yay! Now these match, so we can take the arguments off. X equals 64 to the 2/3. Now we just have to simplify this. Remember, there are two ways to understand this calculation. We can either take 64 and we can square it first, and then we can find the cube root of it, right? Because we would multiply these two together, right? We'd be using our power rule for exponents. We'd multiply that. 2 times 1/3 is 2/3. That's what we're starting with. So this is one way to simplify this. The other way is to say, instead of squaring it first, let's take the cube root first, and then we'll square whatever that is, okay? So again, 1/3 times 2 gives us the 2/3 back, but we can look at this either way we want. And my preference is always to say, make a number smaller before you make it bigger. This one I don't like because I don't want to square 64 and then try to find the cube root. I'm making this big ugly number and then I'm going to try and whittle it down? No. No, no. That's not the fun way. This way, I make it smaller first, then I square it. So I prefer this one. And my rule of thumb here is make a number smaller before you make it bigger. Okay, so this is the one I'll use. Cube root of 64 equals 4, and then squared, or my final answer is x equals 16. Yay. Okay, so this one was the power law used with a this one had a whole number exponent. This one is the one that had the fractional exponent, and that just makes it a little bit more of an interesting calculation. Okay, so our rules, once again, let me remind you because, oh gosh, it's so hard to remember. First, make each side equal to a log function, a single log function. Use the laws of logarithms to mush the pieces together or to pop a coefficient up. And then once they're equal, both equal to logs, then you can pull off the arguments and solve. Okay, that is all we're going to say about logarithms for today. I think that's quite enough, don't you? Now we're going to go back to the talk we've been having about functions, about composing functions. Remember how we learned that like you have an f of x and you have a g of x and you can add them together, you can multiply them, you can subtract them, or you can make the functions eat each other, right? We've done all of this business. Well, we're going to play with that idea again today. And this time we're talking about what we call inverse functions. Now this is true for any inverse functions, but let's say that you have some function machine and we'll just call it the f function. And let's say you take an input named a and you put it through this function, and what comes out we're just going to call b. Now, what if you have another function? We'll call this one the g function. And in this one, we're going to put in a b, and we're going to get out an a. All right? So it undoes, the g function undoes, or it does the inverse of what the g function does. So we would call these two functions, because they undo each other, we'd say the f of x and g of x are inverse functions. And then here comes an even crazier statement of truth. If you take the f function and let it eat the g function, you should get x, if they're truly inverse function. And then if you take the g function and let it eat the f function, you should also get back x. If it passes this test, then you know that these functions truly are inverse functions. And so that's the problems we're going to do. And we call this process computing the composition of a function. Okay, so that's a fancy name for what we're doing here. So in the problems, John might toss that expression at you. Compute the composition of this function. That means do this, all right? And I'll show you how to do that in just a minute. All right, so basically what we're doing is saying, here's a function f, here's a function g. Test it and see if you get this pattern of what we put in here, we get out something. Then if we put that into the other one, then we should get the original thing back, right? That circle, so to speak. All right, so let's take a look at how we do this. And I'm gonna write this down again. This is the idea that helps us compute compositions. If you put one function inside of the other, you should get x. And then if you reverse the order of that, you should also get x. Okay, let's look at an actual problem so this will not seem so ridiculous to you. Most students find these problems kind of fun and kind of easy. Okay, the f of x, here's our first function, equals 1/3 x minus 3. And the g of x is 3x plus 9. Sometimes students think they can figure it out just by looking at it. Don't waste your time. It's crazy. Don't do that. All right. So what we're going to do is first we're going to take the f function and put the g inside of it. Okay, so f eating g is going to be 1/3, and then we'll put a big gap here, minus 3, right? That's the f function. But instead of x, we're going to put the g of x in where the x goes. So this will be 3x plus 9. Make sense? F, we can see this as f eats g. And it was kind of like this, right? That's how we wrote that before. That doesn't say fog. It's that circle. Okay, so they all mean the same thing. So now what we want to do is simplify this. So I'm going to distribute this across. 1/3 times 3 is just 1, x, plus 9 divided by 3 is 3, minus 3, that's this part. Well, that equals x, doesn't it? Okay, that's really good. And so we know now that if you put the g function into the f one, we compute the composition. That works out beautifully. Now let's make sure it works the other way. So now we're going to go, the g has the f function inside of it. So we start by writing out the g function, 3 and then something plus 9. And then the f function goes inside of it. 1 over 3x minus 3. Okay, now we'll distribute again. 3 times 1/3 is 1, so this becomes x. And this is minus 9, right? 3 times minus 3. And then plus 9. And look, there it is again, x. So we just computed the composition. And John said, show that f and x are inverse functions by computing their compositions. So what we can do, here's the way I like to show that. Circle both of these and draw the arrow that connects them to show that you computed the composition of each one of these functions and they match. Not that bad, right? Kind of satisfying, kind of fun when it all works out. Okay, and then we just have one more of these to do. Sometimes the only thing with these problems that can get hard is these functions can get kind of crazy. The next one that we do is going to be a little more complicated. Sometimes John gets a little carried away with how crazy he makes them, and then we have to sort them carefully. So let's try example 40.6 and see if he can throw us. Show that f of x equals 1 over x minus 3, and the g of x, incidentally, it doesn't have to be just f's and g's, but that's what's common, equals 3x plus 1, and the whole thing is over x. So this is going to get a little messy, isn't it? It's going to get a little crazy. All right, so let's try the first one. F eats the g of x. So, okay, so we're going to do 1 over something minus 3, right? That's the f function with a hole in its x, and then we plug the g of x in. 3x plus 1 over x. All right, so we have to simplify this somehow. So we're going to use our complex fraction knowledge to sort this out. In order to be able to do this subtraction, we're going to have to multiply this number by x over x, right? So that we'll have matching denominators. And that will give us 3x plus 1 minus 3x over x, right? Okay. Then these two cancel each other, so we just have 1 over x. So then I'm going to multiply that by its reciprocal, x over 1. And then I'll multiply the top by x over 1. This all reduces down to 0, or 1 rather, not 0, because then we would have an imploded universe. This goes down to 1. Up here on the top, it simplifies to 1. Okay, there's my squiggle to show, look, I did it on the top. I can circle it, that's easier, it shows up a little better. Now we're going to do the other one, g eats the f of x. So we start by laying out the g function. 3, that's where the x will go, plus 1 over, oh look, we have to have 2 x's in this one. So this is 1 over x minus 3 times the quantity, or over 1 minus x minus 3. Wow, this is a lot, isn't it? This is very dramatic. Okay, so this then becomes 3 over x minus 3 plus 1 all over 1 over x minus 3. Okay, so we're having to call in our complex fraction work. I'm going to flip this. Oh, I'm sorry. X minus 3 over 1. So I want to multiply this whole thing by x minus 3 over 1. In order to do that, I have to make these denominators match first. So this is going to be x minus 3 over x minus 3. Okay, so let's see. The bottom is gone. This is going to be, this is a minus sign. I'm written it over the 1. So the numerator of my new fraction is going to be 3 plus x minus 3. Second, I'm just going to have my book floppy for a second. 3 plus x minus 3, and all of this is over x minus 3, and then I'm multiplying it by x minus 3 over 1, because that is what I did to, that's the reciprocal of the old denominator, and I turned it into a 1, right? But here's the top and bottom of that, so I have to multiply the numerator by that chunk as well. Okay, whew, we're almost there. 3 minus 3, those cancel, and I get x over x minus 3 times x minus 3 over 1. Those cancel, x. That's my final answer. And now to connect, this is going to be very dramatic. I'm excited for it though. I'm going to take my arrow, and it goes all the way over here and points to that x. So we had a little drama in our simplification there, but we were able to compute the composition and show that these functions f and g do indeed both simplify to x. If they don't, by the way, and I'm trying to think, I don't know if there are examples where you don't each get them coming down to an x, but if both of these functions don't come down to a single x, then they're not truly inverse functions. They're just random functions that are chilling together, but they're not inverse because they don't have that special property. Lesson 40 is done. Look, week 11 is done. And here's one more abbreviated homework lesson for your Thanksgiving week. Homework for lesson 40. I want to make sure I'm just looking at the problems because I want to make sure that you get. Okay. I'm going to have you do 3, 5, 7, 9, 11, 13, 15, and 17. Okay, so it's 8 problems of the odds, kind of out of the middle of the lesson. But this gives you a nice assortment of things that we've learned fairly recently. A few word problems, not all word problems. It's a nice mashup. Okay, to go with your mashed potatoes. Okay, lesson 40 is complete. There's your homework. I enjoy it. Next week, the week after Thanksgiving, which is the week coming up, we are going to use the unit circle to organize all this information in our trig worlds that has come exploding into our lives lately. If you don't have a copy already of a blank unit circle, then I'm going to put a link in this video description that will send you to getting one. And I need you to print yourself at least 5 hard copies of the blank document, and then I will teach you next week how to fill it out, all right? So the link will be in this description as well as the one next week. Okay, thank you, goodbye.